Well, hello again, everyone. It's Nick, of course, from Engineering Today. Thank you for joining me today. It's a wonderful Thursday. Oh no, it's a Wednesday. It's a wonderful Wednesday here in sunny Midwest. The lab is great today. It's not raining anymore. Yesterday was the first actual day of sunshine. Another great day today. And I'm ready to start talking about everyone's favorite, computer networks. Isn't this going to be fun? So what did we do last time when we talked about computer networks? So I remember talking about the different kinds of networks, getting some initial terminology out of the way. Then we went over things like the OSI model and the TCP IP, or the internet model. And we went into brief detail about those. Now this book mainly covers TCP IP, which is very common. So that's going to be a common theme throughout this book. What else did we cover? Did we cover anything else? We covered some basic principles, some basic rules of thumb when designing a network. We want to know who we're designing a network for. So if we're going to do something network engineering related, we have to know, okay, are we designing it for a city scale? Are we designing it for, some end user someplace? Brilliant. Nice to see you today. Is it a wonderful Wednesday where you live? I have audio playing someplace. I need to turn it off. Here it is. There it goes. Okay. Well, there's nothing better to do than to just get started. So let's see. As a recap of Chapter 1, let's get the highlighter out. So in Chapter 1, we saw a network consists of links interconnecting nodes. So this idea of links, which are these physical connections, and nodes, which are typically things like switches that do some routing for us. We saw that one of the problems that we typically face is how to connect two nodes together. We also introduced some layers of abstraction here. So having the cloud abstraction representing some network where we don't have to worry about, every single point of interconnection. We can just assume we give it some information, we give it some encoded message. In that message, it gets decoded someplace in the cloud. It says, where am I going? What am I sending? Where do I need to access? All that routing is taken care of for us, and we just continue on our merry way. So that's the key idea of abstraction that we typically want to talk about. This is also something that ISPs face, connecting a new customer to the network. So how do we connect more nodes to the ISP's cloud? So a fun task there. It's very easy for us to understand, well, what happens if we have some very set network. Say we design it, we build it, we put it in the ground, or we put it wherever, and it works. Now what happens if we need to discover new devices? So whether we want to do something like a 2-node trivial network with one link, or connect the 1 billionth host to an existing network over the internet, we need to address a common set of issues. So this is, well, physically, how are we going to make that connection? Is this going to be some wired connection? Is it going to be some wireless connection? My ISP still hasn't perfected this, and they're not going to. They have no incentive to. Weren't they also supposed to lay fiber in the United States for everyone? They were supposed to do that. They didn't. So like we said, it could be wire, or it could be something like optical fiber, or something else such as, electromagnetic radiation, but we'll just call that radio waves. And then of course we need to talk about size, so whether it's an office building, whether it's a city, whether it's a county, whatever we're talking about. Connecting two nodes with a suitable medium is only the first step. 5 additional problems we must also address is, okay, well, first, how are we going to encode bits? So we don't want to just send raw streams of bits. That's dangerous. What happens if we lose a bit? Do we just completely lose track of where we are? So we want some kind of encoding to help us with that. So then this typically also brings up this idea of framing. We don't just want to send some big long stream of data. We generally want to put it into organized chunks. And so these are typically called frames or packets, depending on what protocol you're using. But the idea is the same. We group bits together that are encoded into packets. So then the other thing that we want to talk about is error detection. So not only do we want to organize data by encoding it and putting it into packets, we want to make sure that if something goes wrong someplace, we can still recover. So this is this idea of error detection. And if we can't recover, we still want to know, well, we lost a packet, something went wrong with it. Either it wasn't delivered or it was delivered, but some of the data was corrupted. So yeah, the fourth issue is making the link appear reliable, in spite of the fact it corrupts frames from time to time. So how do we abstract away these errors? And then, let's see, finally, for those cases where the link is shared across multiple hosts, which is typical of something like a wireless link, it's necessary to mediate access to the link. So this is the media access control. So if we have many users using the same thing, how do we determine or have some kind of fairness between them? So although these 5 issues, encoding, framing, error detection, reliable delivery, and access mediation, can be discussed in the abstract, they are very real problems that are discussed in different ways by different network technologies. So, if we're talking about, this is my first time going through a computer networks book, but I've learned about some computer networks in the past. So if we talk about something like PCIe uses something called a 128/130 encoding, which means they take 128 bits and then they encode it into 130 bits. But something like SAS, which is it's a type of hard drive. It stands for Serial Attached SCSI, so it's typically used with hard drives for server applications. They use something called 8B 10B encoding. So they take 8 bits and they encode it to 10 bits. Let me make sure I'm keeping track. So PCIe does 128/130. I think SAS 3 does 8B 10B. Oops, that's a D. 10B. And then I think SAS 4 does 128/150. Now, why they do 128/150, I have no idea. Nobody was able to give me a clear answer to that. And I was in a training on the SAS protocol, and no one could explain to me why they would do 128/150. But that's okay. We don't care about that. So there's many different ways. It just depends on what protocol you're using. So let's jump right in. Enough background. Idra, nice to see you today. It's a wonderful day. Idra, you're in Europe, right? Listen, I think the streams, I think we're going to try something different. I think we might try the early morning streams for me. That way I'm not having to run and catch the bus and almost miss the bus. So I might be streaming at 4 a.m. my time. So that donation thing for coffee will be even more relevant at that time. You're glad at least the experts know? I mean, I feel like they don't know. I mean, I feel like they could have easily just done 128, 130. But for some reason they decided, no, let's do 128, 150. I forgot what the organization that does that standard is, though. I don't know. I took a training from... I have a certificate. It was like a $10,000 course that I took that was paid for by Dell when I worked there. I think it was like $7,000 or $10,000 for like 3 days. It was ridiculous. So as we saw in Chapter 1, networks are constructed from two classes of hardware, nodes and links. No, listen, Idra, that's the way that corporate training sessions cost. I'm pretty sure coding boot camps probably cost about the same, but this is like corporate training stuff. They're ridiculous. If you become a subject matter expert in those fields, you can make so much money by doing trainings for companies. And the companies not only pay you for the training, like $7,000 to $10,000 per head, but generally you have a minimum of like 15 people have to take the training, and then they fly you out and pay for your accommodations. Yeah, it was what was it? It was a 20-hour training, so it was 2 full days, and then it was a half day. Okay, so we talked about how the building blocks of networks are nodes and links. And so we're going to focus on what makes a useful link so that large, reliable networks containing millions of links can be built. So we're going to be talking about the link in this chapter. Okay. While the operators of large networks deal with links that span hundreds or thousands of kilometers, connecting refrigerator-sized routers, the typical user, the network encounters links mostly as a way to connect a computer to the global internet. So typically when we think of a link, we think of something like, I don't know, an Ethernet cable, right? So like an Ethernet link in the office, building, or university. For the increasingly large and fortunate size of the population, we can even have something like a fiber optic link provided by some telecom company or ISP. So if we skip down to figure 2.1, 2.1 illustrates various types of links as seen by the typical end user of today's internet. On the left, we see a variety of, let's go ahead and look at 2.1. So here we have the typical links that some user would see. So this would be something like fiber optic or Ethernet. Then we have things like, some cellular connection or Wi-Fi, all kinds of things. And then, we'll see that there's different kinds of links depending on what we're going between, and that sometimes the difference between, the links that a user sees can be different from the links that the people in charge of the network or creating the network see. So we'll see a lot more fiber optic and high bandwidth type things over here, while over here fiber optic is a luxury that the telecommunication companies decided not to build in the United States for some reason, even though they were paid for it. So we'll see more Ethernet and wireless on this side. Okay. So of course, there's some links that connect routers together inside the ISP, and a link that connects the ISP to the rest of the internet. Now we always put the rest of the internet in quotes because what is the internet really? It's just a bunch of connections of these same type of nodes and links. So when we talk about the rest of the internet, it's really just an abstraction for more groupings of these types of things. Okay. So how do we make all these different types of link look sufficiently alike to the end users or routers? So we want some kind of consistency. Conferences generally run $1K a ticket. Yeah, GTC costs so much money. You can get a lot. You can go there a lot cheaper as like an academic, just because They usually give student discounts, and sometimes they'll even give you a free ride if you're a professor. But for industry people, a lot of times it's, you're 1K, 1.5K. So essentially, we have to deal with all the physical limitations and shortcomings of links that exist in the real world. So we sketched out some of these issues in the opening problem statement for this chapter. So the first issue is that links are made of some physical material that can propagate signals. So things like radio waves or other sorts of electromagnetic radiation. But what we really want to do is send bits. So it's all fine and well if we can just, send radiation across some spans, right? But, a computer works in bits. When we send information to another side for another computer to read, it has to be in bits. So how do we do that? So we'll look at how to encode bits for transmission on a physical medium, followed by other issues mentioned above. Okay, so let's look at classes of links first. So while most readers of the book have probably encountered at least a few types of links, I think everyone here has probably used Wi-Fi or internet or their cellular link at some point. It will help to understand some of the broad classes of links that exist and their general properties. So for a start, all practical links rely on some sort of electromagnetic radiation propagating through a medium. So medium is just whatever space it's going through. So whether or not it's, some cellular thing or some satellite thing, and it's going through space and the atmosphere, that's what we're talking about when we mean medium. So one way to characterize links, then, is by the medium they use. So typically copper wire and some sort of DSL line and a coax cable, optical fiber, as in both fiber to home services and then long distance links, and the internet's backbone, or these more short distance air/free space wireless links. So yeah, it's one of the interesting things that I was hearing about when I was visiting another university. When I was visiting that university, I was talking with some guy that worked in the wireless area, and he was talking about, everyone kind of knows that the 2.4 gigahertz spectrum is pretty crowded now. There's a lot of traffic. And so they were talking about the challenges of moving to 5 gigahertz and the differences of using high frequency versus low frequency. And I think one of the big problems is that everything just stops high frequency. So once you get to the 5 gigahertz spectrum, you're basically relying to almost having a line of sight between the user and the antenna, which is not great. Because typically you want some more flexibility, and I'm not an antenna guy. I'm not a communications guy, so I don't know the science behind all of it. But I seem to remember him saying things like even things like trees were an issue in the 5 gigahertz spectrum because just the stump itself, something like a 2.4 gigahertz wave could pass through it or something. But a 5 gigahertz wave would just get stopped. So another important link characteristic is frequency, measured in hertz, which is just 1/seconds, with which the electromagnetic waves oscillate. The distance between a pair of adjacent maxima or minima of a wave, so typically measured in meters, is called the wavelength. Since all electromagnetic waves travel at the speed of light, which in turn depends on the medium, that speed divided by the wave's frequency is equal to its wavelength. There's been good improvements to router-to-router switching. It helps a lot. Yeah. I mean, that seems like it's high frequency is a problem in many things. It's a big problem on processors, mainly because of power. I don't know how much of a power concern it is for communication, but I know power doesn't scale linearly. I think it scales exponentially on a processor, so it's typically pretty bad. Okay. So we've all seen the example of a voice-grade telephone line which carries continuous electromagnetic signals ranging from 300 hertz to 3300 hertz. So here's an interesting thing: the 300 hertz to 3300 hertz. This is the range of human hearing, isn't it? I think the lower end of the range of human hearing is like 200 or 220, and then the upper range, I don't exactly remember what it is. Actually, the upper range might be something like 5400, maybe. But that's getting pretty high. But the reason why it's this range is typically because this is the most common range for human hearing. It's a little bit above the minimum and a little bit below the maximum. So, this is good because generally you can think of it as a bandpass filter, where all the low signals, we're not going to propagate them. All the super high signals, we're not going to propagate them. And this is basically human voice, typically. Okay. So what do they do here? So they're dividing the speed of light in copper by frequency. So they're going 2/3 the speed of light is how fast. Yeah, that seems pretty typical. Yeah, so that's the thing. So people generally go, it's like, oh, electricity moves at the speed of light. Well, not really. The argument is usually made with electricity. So when you're talking about how long it takes to get from like one side of a PCB to the other side of a PCB in a copper trace, there's a lot of things you have to keep in mind. So 2/3, I think, a pretty relative number of how long it takes like light to travel in the medium like copper. So this is generally like electricity. So 2/3 times 3 times 10 to the 8th divided by 300 hertz is, let's see, this is 667 times 10 to the third. 10 to the third is 10 squared is 100, 1,000. So this is pretty long distance. This is 667,000 meters. Pretty wide or long wavelength. So generally, electromagnetic waves span a much wider range of frequencies, ranging from radio waves to infrared light to visible light to X-rays, gamma rays, etc., etc. So where's 2.2? So here's the spectrum graph that we've all seen many times before, where we talk about what we actually see, which is in the visible light spectrum, and then all of these other things in here, things like infrared, things like microwaves, radio waves, things that we typically care about. So fiber optics, they can use very, very high frequencies, which is good for us because it means that they're very quick. It means that we can encode a lot of data in a very short time span. Then we have things like satellite, coaxial cables. We see the difference between the AM and the FM bands, TV, and then terrestrial microwaves. So far we understand a link to be a physical medium carrying signals. Such links provide the foundation for transmitting all sorts of information. So basically what we've learned so far is that we can send electromagnetic radiation through some physical link. So including the kind of data we're transmitting, binary data, ones and zeros, that's what we care about. So we have to encode this into the signal. So we have to remember that if we're sending some kind of radiation doesn't come in a 1 or a 0. So we have to do some encoding. So the problem of encoding binary data onto electromagnetic signals is a complex topic. To help make the topic more manageable, we can divide it into 2 layers. So what are these 2 layers? So the bottom layer is going to be modulation, at which we vary the frequency, amplitude, or phase of the signal to affect the transmission of information. So a simple example of a modulation is to vary the power or amplitude of a signal. Intuitively, it's equivalent to turning a light on and off. So we can either pump up the amplitude or we can nullify or decrease the amplitude. Because the issue of modulation is secondary to our discussion of links as a building block for computer networks, we simply assume that it is possible to transmit a pair of distinguishable signals. This means that we don't really care how it's being generated at this point, or really at any point. That's a problem for some other engineer. We can just basically assume that there's a way to transmit a 1 and a 0 no matter what medium we're working on. Let's see. Think of them as high signal and low signal, and we consider only the upper layer, which is concerned with the much simpler problem of encoding binary data onto these signals. So section 2.2 discusses such encodings. Okay. So here we have typical bandwidth of common services connected to your home. So we have dial-up being at, a measly 28 to 56 kilobits per second. ISDN, I'm not sure what ISDN is, but 64 to 128 kilobits per second. DSL, 128 kilobits per second, up to 100 megabits per second. Not bad. Cable TV, getting a little bit better. Not as high of a range in the bandwidth, but a better lower bound. And then we have fiber to home, 50 megabits per second to 1 gigabits per second. Now, remember, this book was written in 2010, 2011, so it's been 8 years or so. So, maybe these numbers aren't quite accurate anymore. Or we don't even care about dial-up anymore. There are still people that use dial-up, but we don't really care about dial-up anymore. I think AOL was making like $1 million a year in 2013 or something from dial-up still. From like customers still paying for AOL internet. Absolutely insane. So finally, in addition to last mile and backbone links, there are links that you'll find in a building or campus referred to as local area networks. So Ethernet, described in 2.6, has for some time been the dominant technology in this space, having displaced token ring technologies after many years. While Ethernet continues to be popular, it is now mostly seen alongside wireless technology. So basically just saying, when we're not talking about how do these massive networks communicate with each other, the end user mainly sees wireless and Ethernet. Okay. So now that we've got some of the boring stuff out of the way, we talked about, or I hate to say boring stuff, but we got some of the more foundational topics, going over, what's a medium, what are the big problems you want to cover. We can talk about some more interesting things. So different types of encoding, things like NRZ, NRZI, Manchester encoding, and then 4B, 5B, which seems like 8B, 10B. In fact, I think 4B, 5B is actually 8B, 10B in some respect because it has the same ratio. So, 20% of the bits are wasted for encoding. And it's the same thing for 8B, 10B. This is just 4/5. So these might actually be the same protocol. Well, they might be just two different names for the same thing. So the first step, turning nodes and links into usable building blocks, is to understand how to connect them in such a way that bits can be transmitted from one node to another. Okay. The task, therefore, is to encode the binary data that the source node wants to send into the signals that the links are able to carry. Okay. And then, of course, we want to decode that information. If we're sending data, at some point we're going to want to do something with that data. Otherwise, we're just, we're yelling into an empty room. So we ignore the details of modulation. Of course, we talked about that earlier. And assume we're working with two discrete signals, high and low. So in practice, these signals might correspond to two different voltages on copper-based link or two different power levels of an optical link. So typically it's rather interesting because you can see these transmission protocols in something like an oscilloscope, and basically what you want to see is I forgot exactly what this is called. I think this is called like an oxeye or something. And basically, you want to see some like clear differentiation in this region. I'll have to find that presentation that I have over SAS 3.0. But yeah, so typically this could be something like, I don't know, going to an extreme, we could consider this as like 1 volt and 0 volts. In reality, it's much lower than that. And the time scale here is actually incredible. The time scale here could be something like, I don't know, like 50 picoseconds. Something absolutely incredible. I'll have to get that presentation out. I know where I have it saved. I just haven't looked at it in years. Most of the functions discussed in this chapter are performed by a network adapter, a piece of hardware that connects a node to a link. The network adapter contains a signaling component that encodes bits into signals, and the sending node, and decodes signals into bits at the receiving node. So we have a sending node that we can do some encoding, and then we have a decode portion that can decode the incoming encoded signals. So this is illustrated in figure 2.3. So some signaling component is the thing that's, it's really doing the sending of the data. We have some adapter that, helps us translate some code into what we need, and then we have the node itself, which is doing the switching to wherever the signal needs to go. And then the bits travel across this medium. So it looks like we're going to start with NRZ, which is non-return-zero. So let's return to the problem of encoding bits onto signals. So obvious thing to do is to map the data value 1 onto the high signal and 0 onto the low signal. This is exactly the mapping used by the encoding scheme called, cryptically enough, non-return-to-zero. For example, figure 2.4 systematically depicts the NRZ encoded signal that corresponds to the transmission of a particular sequence. So, simple enough, probably the most simple encoding we can do. If the bit's 0, we're here at, say, 0 volts. And if the bit's 1, we're up here at, say, 1 volt. Or maybe it's 0.7 volts or something. Okay, simple enough. We go high when the bits are high. We go low when the bits are low. The problem with NRZ is that the sequence of several consecutive 1s means that the signal stays high on the link for an extended period of time. And we'll see that there's very complicated protocols that, these patterns of, lots of repeated 1s. I need to pull up this presentation. They're actually very, very bad because they can cause some like electromagnetic interference. And so you typically don't want, I think something like 8B, 10B encoding, or what they use for SAS encoding, I think it actually limits you to like 3 consecutive 0s or 3 consecutive 1s, and then it does something to interrupt that consistent sequence. It's incredible. So similarly, several consecutive 0s means the signal stays low for a long time. There are 2 fundamental problems here, caused by long strings of 1s or 0s. So one is known as baseline wander. Specifically, the receiver keeps an average of the signal it has been so far, and then uses this average to distinguish between a low or high. Whenever the signal is significantly lower than the average, the receiver concludes that it has just seen a 0. Likewise, a signal that is significantly higher than the average is interpreted as a 1. So when we get too many 1s or 0s, the average changes, making it more difficult to detect a significant change in the signal. So this kind of repetition leads us to this baseline, this average, to either start to move upwards or start to diverge and go downwards, depending on if we get long strings of 1s or long strings of 0s. Okay. So what's the second problem? So the frequent transitions from high to low and vice versa are necessary to enable clock recovery. Intuitively, the clock recovery problem is that both the encoding and decoding process are driven by a clock. Every clock cycle, the sender transmits a bit and the receiver recovers a bit. The sender and receiver's clocks have to be precisely synchronized in order for the receiver to recover the same bits the sender transmits. So if we're not synchronized, what can happen if we're not synchronized? Well, we could just think of it, if we're sending bits, say we send like 3 bits, but then to this guy. But this guy over here may be not synchronized, and maybe it only catches the signal maybe here. And then maybe it skips over and this guy comes by, this guy hasn't arrived yet. Maybe it only catches 1 out of 3 bits. So we want some kind of synchronicity. That way, I guess that's a bad example. So we'll think of it more as coming in a straight line. So what happens if we're slightly out of sync? Well, we might just pass over 1 bit in our decoding. So we might just lose this data. So it's dangerous. We don't like that. If you send data, we want it to be received by someone. Okay. You could imagine sending the clock to the receiver over a separate wire, but this is typically avoided because it would cost it makes the cost of cabling twice as high. So generally we want to save money. So if we don't want to just replicate hardware everywhere we have it, we want to be a little smarter. So whenever the signal changes, such as on a transition from 1 to 0 or 0 to 1, then the receiver knows it is at a clock cycle boundary and it can resync itself. But if we have long periods of say one thing, we never really know, okay, well, I know I'm seeing zeros, but how are these differentiated? That becomes less obvious because remember, we're having to synchronize, across some distance. So to address this, there's Nonreturntozero inverted that has the sender make a transition from the current signal to encode a 1 and stay at the current signal to encode a 0. So let's read this again. So has the sender make a transition from the current signal to encode a 1 and stay at the current signal to encode a 0. Okay. This solves the problem of consecutive 1s, but obviously does nothing for consecutive 0s. So NRZI is illustrated in figure 2.5. So let's see what NRZ is again. So NRZ, when we have a 1, we're high. When we have zeros, we're low. So let's see what happens with NRZI. So a 0, we're low. A 0, we're low. We get a 1, we're high. We get a 0, we're low. We get a 1, we're high. We alternate on the 1s, it looks like. Okay. So whenever we get a 1, we transition. And whenever we get a 0, we hold. That's what it's saying. And so let's see what Manchester code is. So an alternative called Manchester encoding does a more explicit job of merging the clock with the signal by transmitting the exclusive OR of the NRZ encoded data and the clock. The Manchester encoding is also in 2.5. Observe the Manchester encoding results in 0 being encoded as a low to high transition and 1 being encoded as a high to low transition. Okay. So let's kind of rationalize this. So it said it's an exclusive OR of the clock and of the bit. So here we have a bit of 0. So in the low to high, we'll be doing a 1 and a 0. So we should get a 1, so Manchester will be 1. Then on the next one, we'll do it again. We have a 0 and a 1, or it's hard to tell exactly from this picture exactly how Manchester coding works. So let's read it again. So observe that the Manchester encoding results in a 0 being encoded as a low to high transition and a 1 being encoded as a high to low transition. So let's just go by that. So 0 is low to high, so 0. So this should be 0, and then 0 again, low to high low for a 1, low to high for a 0, okay, high to low for a 1, high to low for a 1, okay, that makes more sense. So there's also a variant of Manchester encoding called Differential Manchester, in which a 1 is encoded with the first half of the signal equal to the last half of the previous bit's signal, and a 0 is encoded with the first half of the signal opposite to the last half of the previous bit signal. So you see this idea of, it seems like we're just obfuscating our data, but in reality we're doing things to make it more appealing and friendly to whatever medium we're transmitting over. But it is some kind of obfuscation. So the problem with Manchester encoding scheme is that it doubles the rate at which signal transitions are made on the link, because now we're having to do a clock tick for every single bit rather than just have every clock tick just sustain and hold some value of 1 or 0. Now we're using this clock bit for some encoding. So it doubles the rate at which signal transitions are made on the link. So effectively doubling our frequency, which means that the receiver has half the time to detect each pulse of the signal. So the rate at which a signal changes is called the baud rate. In the case of Manchester encoding, the bit rate is half the baud rate. Okay? So the encoding is considered only 50% efficient. Keep in mind that if the receiver had been able to keep up with the faster baud rate by the Manchester encoding, then both NRZ and NRZI could have been able to transmit twice as many bits in the same period. Okay. So the final encoding, where we start to do more of a mix of these two things, is going to be this 4B, 5B, and attempts to address the inefficiency of Manchester encoding without suffering from the problem of having extended durations of high or low signals. So the idea of 4B, 5B is to insert extra bits into the bit stream as to break up long sequences of zeros or ones. Specifically, every 4 bits of actual data are encoded in a 5th bit that is transmitted to the receiver. Hence the name 4B, 5B. So for every 4 bits, we throw in an extra bit there for fun. The 5-bit codes are selected in such a way that each one has no more than 1 leading 0 and no more than 2 trailing 1s, or 2 trailing 0s. Thus, when sent back to back, no pair of 5-bit codes result in more than 3 consecutive zeros being transmitted. So if we kind of draw this out, it says that we can't have some bits ending at a 0, 0. So it says that we have a maximum of this, so we know that this bit here must be a 1. And then we also know that starting out of the next block, we can have a 0, but we know the next bit has to be a 1. So we have a maximum of 3 concurrent zeros here. Okay. The resulting 5-bit codes are transmitted using the NRZI code encoding, which explains why the code is only considered about consecutive zeros. NRZI already solves the problem of consecutive ones, since we already go from high to low or low to high, and we kind of alternate with the ones. So note that 4B5B encoding results in 80% efficiency, so not bad. However, nowhere near as good as something like 128-130, which makes me beg the question, why did they not use 128-130 in SAS4? Seems like a no-brainer. So table 2.2 gives the 5-bit codes that correspond to each of the 16 possible 4-bit data symbols. So where's table 2.2? Okay. So we have the 4-bit data code as 111, and then we'll tack on a 0 here in this case, and 001, we make sure that we can't have more than one leading 0, so this has to be flipped to a 1, and we can't have more than 2 ending 0s, so this gets flipped to a 1, and the others are fairly trivial. Remember, this is just some encoding standard that someone created, so if it is not intuitive or you can't find out some mathematical equation, well, you don't need to. It was made up. Okay, so that gives the 16 possible 4-bit data symbols. Notice that since 5 bits are enough to encode 32 different codes, and why we're only using 16 of these for data, there are 16 codes left over we can use for other purposes. So things like all 1s or all 0s, or 00100 can be interpreted as a halt. So now we have some free space here. So we have 16 possible symbols just for data, but now we have 16 to do any other kind of arbitration tasks for us. So saying whether a line's idle or not, like we said, or if a line's dead, or if there's a halt someplace. Except apparently only 3 of these are used, and the remaining 13 codes, 7 of them not being valid. Okay, and the other 6 do some kind of control symbol, or they represent some kind of control symbol. So it gives us a little bit of leeway. So let's look at framing now. So we talked about how do we put bits on a line, and how do we do it to respect what medium we're working on. So now let's talk about something framing. So how do we sequence these bits together in a way that makes sense into something discrete, not streaming? So now that we've seen how to transmit a sequence of bits over a point-to-point link from adapter to adapter, let's consider the scenario in figure 2.6. So where is 2.6? So you have bits flowing between adapters, and then over here, these bits are going to represent frames. So we send a frame, the frame gets translated into a stream of bits, and then it gets repackaged as a frame on the other side. Okay, so from chapter 1, we saw that on packet switch networks, or that these networks are packet switched and not bit streams. So it's the network adapter that enables the nodes to exchange frames. Let's see. So when A wishes to transmit a frame to node B, it tells the adapter to transmit a frame from the node's memory. This results in a sequence of bits being sent to the link that represent the frame. Then the adapter on B has to collect together the sequence and has to repackage them as the same kind of frame. So how do we address something like the framing problem? So we'll see several different protocols, and showing that there's a lot of room in the design space where we can create our own type of protocol. Okay. So we have byte-oriented protocols. So BiSync, PPP, or DDCMP. So one of the oldest approaches that has its roots in connecting terminals to mainframes is to view each frame as a collection of bytes, characters, rather than a collection of bits. So bytes are typically 8 bits. Such a byte-oriented approach is exemplified by older protocols, so binary synchronous communication, developed by IBM in the 60s, so a while ago now, almost 60 years ago now. Digital Data Communication Message Protocol, DDCMP, used in Digital Equipment Corporation's DECnet. The more recent and widely used point-to-point protocol provides another example of this approach. So we're talking about these bytes. Instead of just talking about bits now, we want to think of our transmissions in terms of bytes. So what's a sentinel-based approach? So figure 2.7 illustrates the bisync protocol's frame format. So where's 2.7? Okay. So I'm assuming these are 8 bits. So we have, it's probably best we just go over that and so we understand what these abbreviations are. Okay, so above each field is the number indicating the length of that field in bits. So note that the packets are transmitted beginning from the leftmost field. Okay. So it uses special characters called sentinel characters to indicate where a frame starts and ends. So typically when we're sending groupings of bits, we want to know, okay, is this the start of a frame? Is it the end of a frame? What determines an end of a frame? So these are done by the synchronize sections or a synchronized character. The data portion is contained between 2 or more special characters, STX standing for start of text and ETX for end of text. We have a header here denoted by start of header. That's similar to this start of text field. The problem with Sentinel approach, of course, is that the end of text character might appear in the data portion of the frame. So Bisync overcomes this problem by escaping the ETX character by preceding it with a DLE, so a data link escape, whenever it appears in the body of the frame. So this basically just says, if we encounter some text that may look very similar or exactly like a character that does something special, we just ignore it if it's in this section. So here we have 2 syncs at both 8 bits. Then we have a start of header, or header itself, a start of text, some body of, it looks like arbitrary length. I'm not sure what the standard size is. I know for SAS, I think it was the frames were 2K size. Then there's the end of text, and then CRC, which is going to be some kind of synchronization or cyclic redundancy check. So this is kind of a error detection mechanism. Okay, so the frame formats also include this for error detection. So we'll talk about error detection more in 2.4. So the frame finally contains additional header field that is used for, among other things, the link level reliable delivery algorithm. Example of these algorithms are later in 2.5. So we'll talk about the things that are really making up these frames later. But the key idea here is that we're taking our data and now we're organizing it. And not all of our data represents data. Now we pad on some extra bits. So it looks like we pad on 24 bits for synchronization and starting a start of header, some amount for header itself, another 8 bits to indicate we're starting our data. Then we have our data, 8 bits indicating this is the end of our data, and then we have 16 bits to kind of check, hey, did we make a mistake someplace after we transmitted this? So point-to-point protocol, which is more recently used, carries internet protocol packets from various sorts of point-to-point links, similar to Bisync as it uses sentinels and character stuffing. The format for a PPP frame is in 2.8. So here's a PPP frame. So here we have a flag, address, control, whatever protocol, a checksum, and then another flag. So the flags are mainly, from my intuition, are going to be the start and end. The address and the control and the protocol is going to be how we're transmitting this data. Then we have our data itself. We have a checksum to check if we've done any kind of errors. Pepe? Yeah, man. It's a Pepe frame format. The special start of text character denoted by flag is a sequence of bits. So this is 8 bits. The address and control fields usually contain default values and are so uninteresting. So we even ignore address and control because we just use default values in there. Nothing special. So the protocol field is used for demultiplexing. It identifies high-level protocol such as IP or IPX, an IP-like protocol developed by Novell. The frame payload size can be negotiated, but it is 1500 bytes by default. So the checksum field is either 2 or 4 bytes long. So in here it's 2 bytes long, 16 bits. Okay. The PPP frame format is unusual in that several of the field sizes are negotiated rather than fixed. So unlike this original one, this bisync format, everything had the set size of the 8 bits or 16 bits. Some of these things can differ. So the checksum can be 16 bits or 32 bits. So this negotiation is conducted by a protocol called the link control protocol. So they work in tandem, PPP and LCP. LCP sends control messages encapsulated in PPP frames. And then they're denoted by some identifier saying, hey, I know this looks like a PPP protocol message. It's actually LCP. And then turns around and changes the PPP's frame format based on the information contained on those control signals. So this is likely going to be some arbitration at the beginning of some transmission. So generally you do some kind of initial test. You of course want to see if whatever host you're trying to connect to is available, and then you see if it's even on, and then you try to negotiate some kind of communication and set a protocol or set your sizes or your frame format. So let's talk about the byte counting approach. So every CS 101 student knows the alternative to detecting the end of file with the sentinel value is to include the number of items at the file at the beginning of the file. So this says that, hey, why have something at the end that says done when you could just say read or send 20 bytes? So the same is true for framing. The number of bytes contained in a frame can be included as a field in the frame header. So DECnet DDCMP uses this approach as illustrated in figure 2.9. So in this example, the count field specifies how many bytes are contained in the frame's body. So they have space for 2 to the 14, I'm guessing bytes, so 2 to the 14 will be 1K, 2K, 3, or 2K, 4K, 8K. They can send 8K bytes in the body. Is that right? So 2 to the 10 is 1K. 11 bits is 2K. 12 bits is 4K. 13 bits is 8K. So 16K in the body. They can send 16K in this body. So one danger in this approach is that a transmission error could corrupt the count field, so then the end of the frame would not be correctly detected. So we may say, oh, well, the frame says we sent 10 bytes of data, but maybe we sent 30 bytes of data. Well, that's not good. Should this happen, the receiver will accumulate as many bytes as the bad count field indicates, and then use the error detection field to determine that the frame is bad. So this is called a framing error. The receiver will then wait until it sees the next sync character to start collecting the bytes that make up the next frame. So it's possible framing error will cause back-to-back frames to be incorrectly received. Interesting. So let's talk about bit-oriented protocols. So we just talked about byte-oriented ones. So now let's talk about things in terms of bits. So HDLC. So here we're not concerned with byte boundaries, so no more groupings of 8 bits. And we're simply going to view the frame as a collection of bits. So these bits might come from some character set, so like ASCII. There might be a pixel value in an image, or they could be instructions and operands from an executable. So the synchronous data link control, so HDLC, or that's SDLC, developed by IBM as an example of a bit-oriented protocol, and then it was standardized as high-level data link control, HDLC. The following discussion, okay, so let's go ahead and just look at the frame format. So in this case, we have some beginning of sequence, we have a header again, we have some cyclic redundancy code, and then we have an ending sequence in terms of bits, and then we have some body that is just going to be some size of bits. So remember, we're not doing any kind of count field where we just read or write certain amount a count in this body. This can be some arbitrary value now. So let's see if there's anything interesting here. Okay, I don't think there's really anything interesting here. It's simply another protocol, but in this case, we're not grouping things in terms of bytes. We're just throwing bits at it. So an interesting characteristic of bit stuffing, as well as character stuffing, is that the size of a frame is dependent on the data that is being sent in the payload of the frame. It is in fact not possible to make all frames exactly the same size, given that the data might be carried in any arbitrary frame, and any frame is boundary. Given that the data that might be carried in any frame is arbitrary. Okay, so because we have arbitrary data, we can't come up with some set size that we're going to use, because it may not fit. You know, if we try to say we have data that is 2 bits, and say our entire thing we're trying to send on, so let's draw this out. So we have something that's, say this is 10 bits, and say it's all reserved for data. Well, if we have little payloads that are 2 bits, right? Well, we could fit 5 of these in here, and that works fine if these are all 2 bits. Now what happens if we have this same 10-bit thing, but it says we can send arbitrary data? So what happens if we get something that's 3 bits now? So we'll have 3 bits and 3 bits and 3 bits. Ah, what's this? We can't fit another 3-bit chunk in there, so that's why we can't do some set boundary. Okay. So another framing technique, different from byte and bit, clock-based framing. So this is exemplified by synchronous optical network, or SONET. For lack of a widely accepted generic term, we refer to this approach simply as clock-based framing. So Bell Communication Research, Bellcore, and then developed under the ANSI, American National Standards Institute, for digital transmission over an optical fiber. It has since been adopted as the ITU-T. I'm not sure what ITU-T is. SONET has been for many years the dominant standard for long-distance transmission of data over optical links, so things like fiber. The important point to make about SONET before we go any further is that the full specification is substantially larger than this book. That's pretty frightening. Also, SONET addresses both the framing problem and the encoding problem. It also addresses a problem that is very important for phone companies, the multiplexing of several low-speed links onto one high-speed link. In fact, much of SONET's design reflects the fact that phone companies have been concerned with multiplexing large numbers of the 64 kilobits per second channels that traditionally were used for telephone calls. So we'll begin with SONET's approach to framing and discuss other issues following. Okay. So it has a frame that has some special information about where the frame starts and ends, However, it's completely different from there. So there's no bit stuffing so that the frame's length does not depend on data being sent. So the question asks, how does the receiver know where each frame starts and ends? So we consider the question for the lowest speed Sonnet link, which runs at a pretty quick speed of 51.84 megabits per second if we compare that to the other things we were looking at that were in the kilobit range. Okay, so it's arranged as 9 rows of 90 bytes each, and the first 3 bytes of each row are overhead, while the rest being available for data that is transmitted over the link. So let's see. So we have 9 rows, and then we have the first 3 bytes, right? Yeah, the first 3 bytes are overhead. And then the rest of it is reserved for data. So let's make this a cool color. Let's make this like blue. Let's do a light blue. There we go. Okay. However, since bit stuffing is not used, there's no reason why this pattern will not occasionally turn up. Okay. So the first 2 bytes of the frame contain a special bit pattern. So they talk about, well, what happens if there's this pattern within the payload itself. So to guard against this, the receiver looks for a special bit pattern consistently, hoping to see it appearing every 810 bytes, since the frame is 9 times 90, 810 bytes long. When the special pattern turns up in the right place enough times, the receiver concludes that it's a sync and it can interpret the frame correctly. Have you considered being an artist? That looks great. No. Moving on. I'm a great artist. Oops. I'm a regular Matisse. I'm an impressionist. That's what I am. Okay. One of the things we're not describing due to the complexity of Sonnet is the detailed use of all the other overhead bytes. So the other overhead bytes of Sonnet are encoded using NRZ with the simple encoding described in the previous section. However, to ensure there are plenty of transition to allow the receiver to recover the sender's clock, the payload bytes are scrambled. This is done by calculating exclusive ORs, XORs, of the data to be transmitted by the use of a well-known bit pattern. The bit pattern, which is 127 bits long, has plenty of transitions from 1 to 0 so that XORing it with the transmitted data is likely to yield a signal with enough transitions to enable clock recovery. So it looks like Sonnet does a lot of crazy things where it does some scrambling. It uses this completely different format, but hey, it's high bandwidth and it's what we use for fiber. So then it talks about how they multiplex, say, STS1 links, which are that 54 megabit per second links, into a single STS3, which looks like it's 155.25 megabits per second. So, you know, there's ways of kind of splicing these things together to look like you actually have better throughput than you may have. I think back in the day, you used to be able to, shotgun internet connections by actually splicing the cables? Wasn't that a thing that people did? I'm pretty sure people did that. They had like shotgun routers or something. And you would actually get twice the bandwidth. And I think they've even shown that you can do that now, where you can get like 2 separate internet service providers, and you can get 2 different Ethernet connections, and you can actually splice those together to get a better Ethernet connection. Crazy stuff, though. Crazy stuff. But at the end of the day, we're not here to, read the book on a specific protocol. We care about the high-level concepts. So let's talk about error detection. So as discussed in Chapter 1, bit errors are sometimes introduced into frames. What does a bit error look like? Well, if we take some encoding of bits and say this is supposed to be 0, 1, 1, 0, well, what happens if something happens along the line and this maybe turns into a 1? We need a way to be able to tell that we need a way to say, hey, this is wrong. So how do we do that? We typically do that with things called error correcting codes, but detecting errors is only one part of the problem. The other part is actually correcting the errors once detected. But sometimes we get to points where there's so many things wrong with the packet that we say, I can't correct this. Just delete it. Say it's gone. Say we didn't receive it. So the two basic approaches can be taken when the recipient of a message detects an error. So one thing we need to do is we need to notify the sender that the message was corrupted. So that way, we're not just losing data. We're saying, hey, something happened. Please send another copy. I'd really appreciate it. If bit errors are rare, then in all probability, the retransmitted copy will be error-free. So if we say have a 99.99% error rate, how likely is it that the next packet will be, how likely is it the next packet will contain an error? Probably pretty slim. Alternatively, some types of error detection algorithms allow the recipient to reconstruct the correct message even if it's been corrupted. So this is with things like error correcting codes. So sometimes we just check to see if there's a problem. Other times we check to see if there's a problem and try to fix it ourselves. One of the most common techniques for detecting transmission errors is cyclic redundancy check. It's used in nearly all link level protocols discussed in the previous section. So 2.4.3 outlines the basic CRC algorithm, but we want to consider two simpler schemes first, so two-dimensional parity and checksums. The former used by Bisync when it's transmitting ASCII, and the latter is used by Internet protocols. So Internet protocols use checksums, and then when transmitting ASCII, these use two-dimensional parity. So the basic idea, of course, is that we're adding redundant information to the frame that can be used to determine if errors have been introduced. So a lot of times we'll keep a track of, well, every frame is only supposed to have an odd number of zeros, or maybe an even number of zeros. And we can check that if our frame has if our frame's supposed to have an even number and it has an odd number, well, we say, hey, something went wrong. You may not know which bit is flipped, but you know something's wrong. But if you have something like 4B, 5B encoding, well, it becomes a little more clear, because if you get an illegal character combination, you can say, well, that's illegal, and I know that I had a bit flip. Maybe if I flip this bit back, hey, maybe it's fine then. So let's take an example. So if we had the combination 1, 1, 0, 0, 0. Now, under 4B, 5B, we know that we're only allowed to have two trailing zeros. So if we had some information of, well, in 4B, 5B, we know that it has to be, we can't have this combination. So if we had some check in here that allowed us to go, hey, well, this is really the troublemaker. Maybe I can just on my own say, hey, get out of here. You're actually supposed to be a 1, because otherwise you're illegal. So if I can change this and I have 1, 1, 1, 0, 0, a correct frame, well, then I didn't have to ask the sender for another copy of that frame. And so I'm not holding up the entire pipeline. So of course, we could imagine transmitting two complete copies of data. So in this case, we could have, just send the data twice every single time. That way, if one of them's wrong, the other will be right. And then this is just saying, oh, you could just check them together, and if they're different, then something went wrong. So it's a poor idea because, well, we're sending 2 in the number of bits. So fortunately, we can do a lot better than this simple scheme. In general, we can provide quite a strong error detection capability while sending only k redundant bits for an n-bit message, where k is much, much less than n. So on Ethernet, for example, a frame carrying 12,000 bits, or 1,500 bytes, of data requires only 32 bits of CRC, what is commonly expressed CRC32. And that catches the overwhelming majority of errors. Remember, whenever we're working with physical things, we just have to kind of accept that, hey, we're not going to be perfect. But how good can we be? We can probably do a decent job. So we say that the extra bits we send are redundant because they add no new information. Okay. Let's see if there's anything interesting in here. So typically how this works is we apply the same algorithm on a received message that we do on the sent message, and then we compare the results with the one sent by the sender. And if they match, well, then there's probably no errors. But if they don't match, then there might be errors. So this just says that if we take some combination of bits, and this is our cyclic redundancy check, and we say feed it to some algorithm. On the other side, we'll get some other sequence. Now, if we have something in place that's 0, 1, 1, 0, 1, 0, and if this is set on the other side, and we do the same algorithm, and we get, say, 1, 1, 0, 1, 1, is that 1, 1, 0, 1, 1? Yeah. And these are not equal, then we can say, hey, something's wrong, and we didn't need to check the entire data payload. We can just check maybe 32 bits. Okay. So let's go ahead and skip this, and let's get to something more interesting, and let's start talking about this type of error detection. So two-dimensional parity. So two-dimensional parity is exactly what the name suggests. It is based on the simple one-dimensional parity, which involves adding one extra bit to a 7-bit code to balance the number of ones in a byte. For example, odd parity sets the 8-bit to 1 if needed to give an odd number of ones. So if we had something like 1, 1, 1, 0, 0, 0, 1. So here we have an odd number or an even number of ones. So the parity bit, called P, will be a 1. Otherwise, if we had 1, 0, 1, 0, 0, 0, so we have, or 0, 0, 1, then the parity bit would just be 0 because we already have an even or an odd number of ones. So 3 here, 4 here, we add a parity bit, 1, 5. So the parity bit here is just 0. Okay. Two-dimensional parity does a similar calculation for each bit position across each of the bytes contained in the frame. This results in an extra parity byte for the entire frame in addition to a parity bit for each byte. So 2.14 illustrates how it works. So here not only do we check each frame and say, here we're doing an even parity. So if we have 3 ones here, we add 1 to make it 4. If we have 4 here, we add 0 to make it 4 still. If we have 5 here, we add 1 to make it 6 ones, and so on and so on and so on. And then what we do is we run a parity on these bits now. So we have 1, 0, 1, 1, 1, 0. So 4 ones here. So our parity bit is 0. But then we run this on the other bytes as well. So there's 3 ones at this bit position. So this is going to be a 1 to make it even. Let's look at the first bit position. So there's 1, 2, 3. We add a 1 here in order to make it even. And we do that just for every single bit. So we do it horizontally and then we do it vertically. But we add a lot of this, a lot of information here, but we don't add that much overhead in reality. In reality, it's really, what are we adding here? We're adding what? 3, 4, 8. We're adding 14 bits total. Not much really. We're adding 7 bits at the end, and then another 7 bits for the remaining columns. So that's how this two-dimensional parity works. So we use, this idea of the width and the length. Now let's talk about the internet checksum algorithm. So fundamentally different. So it's used by the it's not used at the link level, but it provides some sort of functionality as CRCs in parity. So we discuss it here, and we'll see examples of it later in chapter 3 and 5. So the idea is very simple. You add up all the words that are transmitted and then transmit the result of that sum. The result is the checksum. So it's a simple idea. Now we're just adding things together and we're checking to see if the sum is the same on both sides. So here's a straightforward implementation of the internet checksum algorithm. The count argument gives the length of the buffer measured in 16-bit units. The routine assumes that the buffer has already been padded with zeros to a 16-bit boundary. Okay. Yeah, pretty simple. We just add all the things up together and we just see if they're the same. And if they're not, we know that something went wrong. The checksums don't match. So this code ensures that the calculation uses 1's complement metric rather than 2's complement. So that's what this is doing. It's just doing a tilde. The tilde is a bitwise. It's a bitwise inversion. Okay. Nothing special, pretty boring. So compared to our repetition code, this algorithm scores well for using a small number of redundant bits, only 16 for a message of any length, but doesn't score extremely well for the strength of error detection. For example, a pair of single-bit errors, one of which increments a word and one of which decrements a word, by the same amount will go undetected. So while it's simple and it's consistent, if we had errors that cancel each other out, it doesn't help us. So let's take another example of what we're talking about. So if we have a bit combination such as 1, 0, 1, 1, and we're doing even parity, what happens if both of these bits flip to instead being 1 and 0? Well, if we're doing odd parity, well, we still have an odd number of 1s on both of these. So doing some sort of simple parity is not going to help us here. So that's what they're explaining with this checksum. This checksum says that if you have 2 kinds of errors that cancel each other out, then you could potentially get think that a frame is incorrect when it's actually, or a frame is correct when it's incorrect. So now let's talk about, so we talked about two-dimensional parity, and we talked about checksum. So now let's talk about CRC, or cyclic redundancy check. So it should be clear now that the major goal of designing error detection algorithms is to maximize the probability of detecting errors using only a small number of redundant bits. Cyclic redundancy checks use some fairly powerful mathematics to achieve this goal. For example, a 32-bit CRC gives strong protection against common bit errors in messages that are thousands of bytes long. The theoretical foundations of the CRC is rooted in a branch called finite fields. So the basic idea of it, though, can be easily understood. So think of an n+1 bit message as being represented by an n-degree polynomial, that is, a polynomial whose highest order term is x to the n. Okay. The message is represented by a polynomial by using the value of each bit in the message as the coefficient of the term. So if it's a 1 in the message, it's a 1 here. So for a 7-bit message, this formula or this equation would be 1 times x to the 7, because there's 7 bits. If the next bit is 0, it'll be 0 times x to the 6, and so on and so forth. For example, an 8-bit message consisting of these bits corresponds to the polynomial here. Okay. So we can thus think of the sender and receiver as exchanging polynomials with each other. For the purposes of calculating CRC, the sender and receiver have to agree on a divisor polynomial, c of x. C of x is a polynomial of degree k. For example, c of x equals x third plus x squared plus 1 in the case of k equals 3. The answer to the question, where did c of x come from, is in most practical cases, you look it up in the book. So this is just something that's a standard. Somebody defined these things. We don't need to worry about calculating them for ourselves. There are a handful of divisor polynomials that are good choices for various environments. The exact choice is normally made as part of a protocol design. So Ethernet uses degree 32. Okay. Anything interesting? Okay. When a sender wishes to transmit a message, m of x, that is n+1 bits long, what is actually sent is the n+1 bit message plus k bits. We call this a complete transmitted message because the redundant bits, including the redundant bits, p of x. What we're going to do is contrive to make the polynomial representing p of x exactly divisible by c of x. We explain how this is achieved below. So the key idea is that, let's see, we have an n+1 bit message, m of x, and then we want to include some redundant bits, p of x, but we want to make it so that this combination can be divided by c of x. That's the overall idea. So if it's exactly divisible, that means that we'll retain a 0, we'll get a 0 remainder, but if it's not, we'll get a non-zero remainder, and then that means an error has occurred. So fairly simple. So this can be kind of complicated, but the key idea, or the core idea behind it, is just we're just dividing this message by some set value, some c of x, and if we get a remainder, then an error happened. If we didn't get a remainder, no error happened. Okay. So in this case, there's an error because they get a remainder of, let's see, this is 5. So if this was 0, it would have been correct, but this tells us that, hey, something went wrong. So in this case, this will be m of x and p of x. Here will be c of x. And then this, what was it? M of x and p of x? Yeah. And p just stands for padding. And then here, this is going to be c of x that we're dividing by. And then we're looking for this remainder. Okay. So 6 versions of C of x are widely used in link level protocols, shown in table 2.3. So Ethernet uses CRC32, while HDLC uses CRC-CCITT.ATM, which we'll talk about in Chapter 3. And then ATM uses CRC-8, CRC10, and CRC32. So it has some variance at what it does. So here's those divisors for each of these different protocols. So for something like CRC8, it's an 821, and then you can think of this as x to the 0. So it's an 8210. Here we have a 10-9-5-4-1-0, 12-11-3-2-1-0, and then so on and so forth. And then the CRC calculation using a shift register. Pretty simple. We do some XORing in here. We shift some stuff over in buffers as the message comes in. Okay. So now that we've talked a little bit about framing, and we've talked a little bit about error correction and detection, what makes a reliable transmission? So we don't want to have to, be hard-strung trying to deal with errors all the time. We'd hope that we send information and it gets to the other side most of the time. We want a clean connection. So we bring up this idea of reliable transmission. So as we saw in the previous section, frames are sometimes corrupted while in transit with an error code like CRC that detects such errors. So while some error codes are strong enough also to correct errors, in practice the overhead is typically too large to handle the range of bit or burst errors. So we might get just too many bits that causes too many errors. Even when error correcting codes are used, some errors will be too severe to be corrected, which is what we just said. It's worth noting that reliability is a function that may be provided at the link level, but many modern link topologies omit this function. So furthermore, reliable delivery is frequently provided at higher levels, including both transport, we'll see in 5.2, and at the application layer in Chapter 9. Exactly where it should be provided is a matter of some debate and depends on many factors. So we'll talk about some of the reliable delivery methods here. So the first one that we're going to talk about is stop and wait. And this is a simple automatic repeat request algorithm. The idea is straightforward. After transmitting one frame, the sender waits for an acknowledge before transmitting the next frame. If the acknowledgement doesn't arrive after a certain period, the sender times out and retransmits the original frame. So here we have two different scenarios, or a couple different scenarios. So the first one, the sender sends a frame, then the receiver acknowledges that sent frame. In the second scenario, the sender sends a frame, the acknowledgement gets cut off someplace in between, so the sender just goes, okay, well, I'll check again, and I'll just send the frame again, no big deal, and then it'll receive the acknowledge. Now, in this case, the sender sends a frame that gets lost in transmission, but something happens and it doesn't get there. So it's not that the frame not getting there causes the sender to retransmit, it's the fact that it hasn't received an acknowledge yet. So it's waiting for an acknowledge, it doesn't get the acknowledge, so it just sends it again, and then eventually gets an acknowledge. And then in the ideal case, in the world we want to live in, we send a frame, the receiver says, I get the frame. The sender sends another frame, the receiver says, I got the other frame. So that's the ideal scenario, the ideal case. So sometimes this brings up this idea. So ACK just stands for acknowledge. And a lot of times we use NAC for the exact same thing, but for not acknowledged. Okay. So there's one important subtlety in the stop and wait algorithm. Suppose the sender sends a frame and the receiver acknowledges it, but the acknowledgement is either lost or delayed in arriving. In both cases, the sender times out and retransmits the original frame, but the receiver will think that it is the next frame since it correctly received the acknowledged first frame. This has a potential to cause duplicates. To address this problem, the header for a stop and wait protocol usually includes a 1-bit sequence number. That is, the sequence number is either 1 or 0, and then it should alternate. So in cases such as, I even overlooked this. So in cases like here, where the first frame gets sent but the acknowledge gets missed, it's not resending a frame, it may be sending the next frame. And so what happens over here is the receiver has to know, hey, I received, say, a 0-bit in the header up here. I should be receiving a 1 next. So part of this header and communication back and forth should be kind of synchronizing, hey, am I on a 1, am I on a 0, and it should be alternating. Okay. The main shortcoming of the stop and wait algorithm is that it allows the sender to only have one outstanding frame on the link at a time. So this can often be way below the link's capacity. So consider the example of a 1.5 megabit link with a 45 millisecond round trip time. This link has a delay times bandwidth product of 67.5 kilobits, or approximately 8 kilobytes. Since the sender can send only one frame per RTT, which is return trip round trip time, and assuming the frame size is 1 kilobyte, this implies a maximum sending rate of 182 kilobits per second. So very, very poor. And so they just get this by 1024 times 8 divided by frames time per frame, which is 45 milliseconds, so 0.045. So ideally what we'd like to do is we'd like to have multiple frames get sent at a time. That would be ideal. And then we could have either one big acknowledge or maybe multiple different acknowledges. So let's talk about sliding window. So consider again the scenario where the link has a delay bandwidth product of 8 kilobytes and frames are 1 KB in size. We would then like the sender to be ready to transmit the 9th frame at pretty much the same moment as the ACK for the first arrives. So this allows us to do something called a sliding window. So this time, we're sending, and then when we're sending the next burst, we should be receiving the ACKs for the first burst. So this is called the sliding window algorithm. So first the sender assigns a sequence number to each frame. Okay. The sender maintains 3 variables, send, window size, and gives an upper bound to the number of outstanding unacknowledged frames. So we have to say, okay, well, I'm going to send 3 things. That's the most I'm going to send. So I should only send 3 things that don't have an ACK right now. Okay. So LAR denotes the sequence number of the last acknowledgement received, and the LFS denotes the sequence number of the last frame sent. So it maintains the following invariant, that the last frame sent, the sequence number of the last frame sent minus the, let's see, LAR, which is the last acknowledgement received sequence number, must be less than or equal to the the send window size, illustrated in 220. Okay. So when the acknowledgement arrives, the sender moves LAR to the right thereby allowing the sender to transmit another frame. Also, the sender associates a timer with each frame it transmits, and it retransmits the frame should the timer expire before the ACK is received. Note that the sender has to be willing to buffer up to SWS frames, so as many as the send window size is frames, since it must be prepared to retransmit them until they are acknowledged. So the receiver maintains three variables: the receive window size, denoted RWS, the largest acceptable frame, and then the last frame received. Okay. When the frame with the sequence number, sequence num, arrives, the receiver takes the following action. So if the sequence number is less than the last frame received, or the sequence number is greater than the last arrived frame, or what was LAF? Or LAR? Last acknowledgement received, yeah. Or last acknowledged frame. Then the frame is outside the receiver's window and should be discarded. If LFR is less than sequence number, which is less than or equal to LAF, then the frame is within the receiver's window and it is accepted. So a lot of terms here, a lot of terminology, something that's easier to see in practice. But the key idea is we have set boundaries on senders and receivers, and anything that arrives within these boundaries is okay. But anything that's outside these boundaries, we discard. So, blue good, red bad. Okay. So notice that in this example, the receiver could have sent a negative acknowledgement, or a NAC, for the frame 6 as soon as frame 7 arrived. However, this is unnecessary since the timeout mechanism is sufficient to catch this situation, and sending NACs adds additional complexity to the receiver. So this just says that sometimes we don't need to send NACs because other parts of the network topology takes care of this for us. So if we have timers already that determine whether something will be valid or invalid, there's no point for us to send a message saying invalid if a timer is going to do that already. So another variation of this scheme is called selective acknowledgements. That is, the receiver could acknowledge exactly those frames it has received rather than just the highest number frame received in order. So in the example above, the receiver could acknowledge the receipt of 7 and 8, giving more information to the sender makes it potentially easier for the sender to keep the pipe full, but adds complexity. Okay. So then we have finite sequence numbers and sliding window. So one simplification we introduced into the algorithm, our assumption that sequence numbers can grow infinitely large. So this is this idea that we have sequence 1, sequence 2, sequence 3, all the way to sequence infinity. But we can't really store or represent the number infinity. So what do we do? This has to be stored in a header, so it must be some finite size. So for a 3-bit field, we can store 8 different values, 0 to 7. But this makes it necessary to reuse sequence numbers. So if we reuse sequence numbers, we have to make sure that we're outside of the window where that sequence would be accepted. So this introduces the problem of being able to distinguish between different incarnations of the same sequence numbers. So suppose we have one more number in our space of sequence numbers that we have potentially outstanding frames. That is, our sliding window size is less than max sequence number minus 1, where max sequence number is the number of available sequence numbers. Is this sufficient? So the answer depends on the receive window size. So if receive window size is 1, then max sequence number is greater than or equal to the sliding or the send window size plus 1 is sufficient. If the receive window size is equal to the send window size, then having max sequence num just one greater than the send window size is not good enough. So basically we've developed all of these kind of calculations that define a protocol, and we can do tests to see if the sequence number would be valid or invalid. So we can see if, will this work in our setup, will this not work in our setup. And so this is something that's left to the, I'll say this is left as an exercise to the reader. This is not very interesting content to go over. So they implement a sliding window here. So they type def, swap sequence number, some char, unsigned char, and then they have some sequence num, some acknowledgement number, and then some flags called swap header. Okay. Pretty boring stuff. Let's see when they stop talking about implementing C code. We're not going to just read C code this entire time. That would be boring. Okay. So let's move on to something that might be a little more interesting. So let's look at concurrent logical channels. So the data link protocol used by ARPANET provides an interesting alternative to the sliding window protocol. So the idea underlying the ARPANET protocol, which we refer to as concurrent logical channels, is to multiplex several logical channels onto a single point-to-point link and to run the stop and wait algorithm on each of these logical channels. So there's no relationship maintained among the frames sent in any of the logical channels, yet because a different frame can be outstanding on each of the logical channels, the sender can keep the link full. So more precisely, the sender keeps 3 bits of state for each channel, a Boolean, whether it's busy or not, a 1-bit sequence number to use the next time a frame is sent on the logical channel, and the next sequence number to expect. In practice, ARPANET supports 8 logical channels over each ground link and 16 over satellite. Interesting. All right, so now let's talk about Ethernet and multiple access networks, 802.3. Good old Xerox. So if you guys don't know, Xerox basically invented everything. People oftentimes falsely attribute like Apple and even Microsoft for inventing like the graphical user interface, but in reality that was actually done by Xerox. That was just stolen by Steve Jobs at Apple, and then Bill Gates stole it from Steve Jobs. That's not even a hotly disputed fact. That's literally just what happened. The guy from Xerox actually won the he's dead now. He died like last year. But he was posthumously awarded the Eckert and Mockley Award for his contributions to computer architecture. So, yeah, it was really Xerox that did a lot of the cool stuff back in the day, but they didn't know what they had, and that's bad enough. Okay. So some history. So Ethernet has its roots as early packet radio network called Aloha, developed at University of Hawaii. Like the Aloha network, the fundamental problem faced by Ethernet is how to mediate access to a shared medium effectively. So if we have a lot of Ethernet ports and everyone's plugged in, how do we determine who gets access? So modern Ethernet links are largely point-to-point. They connect one host to an Ethernet switch, or they interconnect switches, hence multiple access. Techniques are not used much in today's Ethernets. At the same time, wireless networks have become enormously popular, so 802.11. And so this is where we're going to get this idea of this fairness or mediation that we have to do. So in the next chapter, we'll go over Ethernet switches more. So we'll focus on how the Ethernet link works. So how does the physical property, or how does physically Ethernet work? So Ethernet segments were originally implemented using coax cables up to 500 meter long, commonly referred to as Cat5 or optical fibers, and in some cases a lot longer than 500 meters. So the cable was similar to the type used for cable TV. Hosts connected to an Ethernet segment by tapping into a transceiver, a small device directly attached to the tap detected when the line was idle and drove the signal when the host was transmitting. It also received incoming signals. The transceiver, so if you ever wonder what transceiver means, it's exactly what it sounds like. It stands for transmitter receiver. So multiple Ethernet segments can be joined together by repeaters. A repeater is a device that forwards digital signals, much like an amplifier. So here we have an Ethernet cable connected by some adapter to a transceiver. So it transmits data and it also receives data being sent by the host. Okay, so it's possible to create a multi-way repeater, sometimes called a hub, as illustrated in figure 2.24. A hub just repeats whatever it hears on one port and out to all ports. So you can think of this as kind of like a broadcast. So it may hear on one port and then it tells everybody here. Okay. So, let's see. So the original Ethernet specification used Manchester encoding, while 4B, 5B encoding, or the similar 8B, 10B that we talked about previously, in my little anecdote, is used today on higher speed Ethernets. So it makes sense. Manchester is just too much overhead. You have to double the clock frequency, and when we already have such high clock frequencies, that's not generally a good idea. Okay, so it's important to understand that whether a given Ethernet spans a single segment, a linear sequence of segments connected by repeaters, or multiple segments connected by a star configuration by a hub. Data transmitted by, what is the software used to write on again? It's external. It's like journal, but spelled with an X. It's free. Oh, I mean, of course it's free. It's just a Linux app. Yep, not a problem. Is that what you... Cogasol, is that what you were looking for me like 4 hours ago? Is that what you were looking for me for? Because you said, Engineering Today, are you here? And then I said yes, but you were already out of chat. Okay. Okay. So let's see. So if we have something like this, we have some bad news, and that's something called collision domain. The multi-axis part of the Ethernet is all about dealing with the competition for the link that arises in collision domain. Okay. Okay, so let's talk about access protocol. So we now turn our attention to the algorithm that controls access to shared Ethernet link. So this algorithm is commonly referred to as the Media Access Control, or MAC. It is typically implemented in hardware on the network adapter. So we don't describe the hardware per se, but instead focus on the algorithm it implements. First, however, we describe the Ethernet's frame and format and address. So, like we've seen many times before, we have a frame. Not too interesting. And then we have addresses. Each host on the Ethernet, in fact, every Ethernet host in the world has a unique Ethernet address. Typically, the address belongs to the adapter, not to the host, but it's usually burned into a ROM read-only memory. Ethernet addresses are typically printed in a form humans can read as a sequence of 6 numbers separated by colons. Each number corresponds to 1 byte of the 6-byte address as given by a pair of hex digits. And here we have a human readable representation of an Ethernet address. Not very interesting, but hey, it's a fun fact that you can share with your friends. To ensure that every adapter gets a unique address, each manufacturer is allocated a different prefix that must be prepended to the address of every adapter they build. For example, AMD is assigned this 24-bit prefix, or 8020. Okay, that's interesting. So each frame transmitted by Ethernet is received by every adapter connected to that Ethernet. Each adapter recognizes those frames, addressed to its address, and passes only those frames onto the host. So you can have a promiscuous model or mode, in which case it delivers all received frames to the host. You can have unicast addresses, an Ethernet address consisting of all ones treated as a broadcast address. All adapters pass frame addresses to the broadcast address up to the host. Okay. So to summarize, let's just look at the summary. Ethernet adapter receives all frames and accepts frames addressed to its own address, addressed to the broadcast address, addressed to a multicast address if it has been instructed to listen to that device, and then all frames if it's in promiscuous mode. It passes to the host only the frames that it accepts. So if it's not in this set of rules, then it won't accept it. So some more on transmission. Talks a little bit about collision here. So in the worst case, A sends a frame at time t. A's frame arrives at B at t plus some time d. B begins transmitting at t plus d and collides with A's frame, and then B's runt 32-bit frame arrives at A at t plus 2d. So this is if we're sharing a single link and we're having to transmit data, we have the risk of colliding because we're sharing some physical medium. So experience with Ethernets. So because Ethernets have been around for so many years and are so popular, we have a great deal of experience using them. One of the most important observations people have made about multi-access Ethernets is that they work best under lightly loaded conditions. Well, isn't that nice? It doesn't help us because this basically says if we don't have many users, it works great. So at utilization over 30%, too much of the network's capacity is wasted on collisions. So if we have to deal with this idea of people sending and trying to receive things at the same time, then we're going to wind up with a ton of overhead because we need to handle this, because we don't want to lose anybody's data. Okay, so now let's talk about wireless. Apparently there's labs that go along with this book, but I don't know what they are. Maybe I should look them up. So wireless technologies differ from wired links in some important ways, but they have some common properties. So issues of bit errors are still of great concern, and even more so because of the noise environment. Like we said earlier, the 2.4 gigahertz band is very crowded, so there could be a lot of interference. So furthermore, you can't go blasting away at arbitrarily high power with a radio transmitter. There are concerns about interference with other devices and regulations to how much power any device may emit at a given frequency. So we have to adhere to some standards. So there's a baffling assortment of wireless technologies, each of which makes different trade-offs. in various dimensions. So one simple way to categorize the different technologies is by the data rates they provide, or how far apart communicating nodes can be. So it can also be what part of the spectrum they work on, be it 2.4 or 5 gigahertz. So in this section, we discuss 3 prominent wireless technologies. And that's going to be Bluetooth, Wi-Fi, and cellular 3G. So 802.15.1, 802.11, which most people are probably familiar with, and then 3G cellular. Okay. So we see that, we have lots of different data rates. So Bluetooth is okay, 2 megabits per second shared. Then we have 54 megabits per second with Wi-Fi. Remember, this is old stuff, so not necessarily recent. This is from around 8 years ago. Bluetooth, short range. Wi-Fi, a little bit better. 3G, pretty good. I mean, we have to get to some cellular tower, so pretty good. However, we're at hundreds of kilobits. Not great. So the typical use is, of course, a mobile phone here, a computer or a wired base here, or a peripheral to a computer like a mouse or a keyboard. And then, of course, cellular is pretty close to DSL. Wi-Fi, it's the wireless version of Ethernet. And then Bluetooth, you can just think of the products you use. A Bluetooth mouse, consider it the analog being a USB mouse. Okay. So one idea that shows up a lot when spectrum is shared along many devices, so when we have a real crowded spectrum, so like the 2.4 gigahertz band, is spread spectrum. The idea is to spread the signal over a wider frequency band so as to minimize the impact or interference from other devices. So for example, frequency hopping is a spread spectrum technique that involves transmitting the signal over a random sequence of frequencies. That is, first transmitting at one frequency, then a second, then a third, and so on and so on. So Bluetooth got a lot of criticism back in the day for doing things like frequency hopping, and I think that was the main motivation why people thought, or not why people thought, while it actually was poor for things like audio. It's because it had to spend so much time doing frequency hopping. I think that was the argument against Bluetooth audio for the longest time, but it's gotten a lot better now. We've gotten smarter about it. The Laughing Man Can. Thanks for following, man. I appreciate it. I don't know if the notification showed up on stream, but I appreciate it anyway. Okay. Let's continue on. Oops. Okay, so the second spread spectrum technique, so we talked about hopping frequencies, is direct sequence. So this adds redundancy for greater tolerance of interference. So this is good. So if we have interference, we don't want to just say, oh, well, if we hop around a lot, maybe we'll be okay. We want some way to go, okay, well, we'll be okay with what we do, but we also want to check, and we want to add a little bit of fault tolerant design when we're making this. So each bit of data is represented by multiple bits in a transmitted signal, so that if some of the transmitted bits are damaged by interference, there's usually enough redundancy to recover the original bit. So we have a little more overhead though. So the transmitted values, known as in-bit chipping code, spread the signal across a frequency band that is n times wider than the frame would have otherwise required. So 227 gives an example of 4-bit chipping sequence. So for something like 1010, we'll add some random sequence, and then we'll XOR the two. So different parts of the electromagnetic spectrum have different properties. So some are better for communication, and some less so. For example, some can penetrate buildings and some cannot. So governments regulate only the prime communication portion, the radio and microwave ranges. So if you ever wondered why, you go into a concrete bunker or you go into like the basement of a building. I don't know if many of you go into concrete bunkers very often. Some of you may, some of you may not. I typically don't. But if you go into the basement of a building, if you ever wonder why you have no cell service, it's because all the concrete, absorbs the signal. And what I mean by absorbs is that it blocks the signal. It can't go through that medium. Concrete is a bad medium for the waves to travel through. So in many wireless networks today, we observe that there are two different classes of endpoints. One endpoint, sometimes described as the base station, that is generally some fixed point. So let's see. So generally have some base station and then client nodes. So here we're talking about, maybe 802.11, so wireless, and the client node is just laptops. But the base station might also be something like an antenna tower or a cell tower. And then the client nodes would be, say, cell phones. So this topology implies three qualitatively different levels of mobility. The first is no mobility for something like the base station, such as when a receiver must be in a fixed location to receive a directional transmission from the base station. The second level of mobility is at the range of a base, such as with Bluetooth. And then the third is between bases, which is the same as like cell phones and Wi-Fi. So these laptops, they can move around, they can be in arbitrary places, and they can, you can run to the other side of the coffee shop and then the other person can take your place in the coffee shop. Doesn't matter. Okay. And then we have something a little more interesting. We have a wireless ad hoc or mesh network. So an alternate topology is a mesh or ad hoc network. In wireless mesh nodes, in a wireless mesh, nodes are peers. That is, there is no special base or station nodes. Messages may be forwarded via a chain of peer nodes as long as each node is within range of the preceding node. So this is some peer-to-peer communication instead. So if we want to talk to, say, this mobile node, we have to send a message and it gets, say, routed through here and then routed through here. Or alternatively, if this isn't available, we may have to go some long way around. Okay. So let's talk at the common, which is 802.11 Wi-Fi. So 802.11 just refers to the IEEE standard for Wi-Fi. For floating point, IEEE does a lot of these standards. So for floating point arithmetic, it's the IEEE 754 standard. I'm sure Bluetooth's is another, what was it, 802.15.1 or something? Something like that. Up here. Yeah, 802.15.1. Okay. So let's talk about some physical properties. So the original standard defined two radio-based physical layer standards, one using frequency hopping, and the other using direct sequence spread spectrum with an 11-bit shipping sequence. And then both provided 2 megabits per second range. The physical layer standard for 802.11b was added, providing up to 11 megabits per second. These three standards all operated on the 2.4 gigahertz band, and so as we know today, this is a very popular band, and it's very busy, it's very packed. So then came 802.11a, which delivers 54 megabits per second. So as technology scales and gets better, we need different standards. We need the standards to evolve. So using a variant of FDM called orthogonal frequency division multiplexing, and it runs on the license exempt 5 gigahertz band. So this band is less used, so there's less interference, but there's more absorption of the signal and is limited to almost line of sight. So this is this idea that I was talking about earlier that, you know, we can use different bands, but they have trade-offs. So with something like 802.11, hey, it's great for us. We can, in the 2.4 gigahertz band, we can put a router someplace and we can access our Wi-Fi that's in the other room. But with something like the 5 gigahertz band, if we have a wall in the way, we're probably not getting any signal. So most recently, 802.11n has appeared on the scene. That was approved in 2009. And it achieves considerable advances in maximum possible data rate using multiple antennas and allowing greater wireless channel bandwidth. The use of multiple antennas is often called MIMO, for multiple input, multiple output. Now, this would be an interesting thing to look up. I'm unaware if MIMO is something that's common or present today. This would be an interesting thing. They said it was approved, but after a standard gets approved doesn't mean that anyone's doing anything with it yet. So it's worth noting that while all the 802.11 standards define a maximum bit rate, they mostly support lower bit rates as well. So 802.11a does 6, 9, 12, 18, 24, 36, 48, and 54. So at lower bits rates, it's just easier to decode. Okay. So the systems try to pick an optimal bit rate based on the noise environment in which they find themselves. So depending on how noisy it is, you may see your bandwidth get better or worse, apparently. That's interesting to know. Interestingly, the 802.11 standards does not specify the approach, but leaves the algorithms to various vendors. So it's just going to depend on whatever, say, router you get, or whatever chip you buy that is a Wi-Fi antenna. The basic approach is to pick a bit rate. Picking a bit rate is to estimate the bit error rate by either directly measuring the SNR, signal to noise ratio, at the physical layer, or by estimating the SNR by just looking at successfully transmitted packets or acknowledgments. So it does some, checking here and there, over time to go, okay, well, I'll check the noise ratio now. Or I'll check, how many packets have I lost recently? Am I losing a lot of packets? Oh, maybe I should slow down. Or if I'm not losing many packets, it might go, oh, I can speed up now. So collision avoidance. So at first glance, it might seem that a wireless protocol would follow the same algorithm as Ethernet, wait until the link becomes idle before transmitting, and back off should a collision occur. And to a first approximation, that's what 802.11 does. But the complication is that while a node on Ethernet receives every other node's transmission and can transmit and receive at the same time, neither of these conditions hold for wireless nodes. So this makes the detection of collisions more complex. So the reason why wireless nodes cannot usually transmit and receive at the same time is that the power generated by the transmitter is much higher than any received signal is likely to be. And so swamps the receiving circuitry. So the reason why a node may not receive transmissions from another node is because the node may be too far away or blocked by an obstacle. This situation is more complex as it first appears. So the hidden node problem, so although A and C are hidden from each other, their signals can collide at B. So we have some overlap here in their signals. Okay. Consider the situation in 230. Okay, suppose A and C want to communicate with B, and so they send it a frame. A and C are unaware of each other since their signals do not carry that far. These two frames collide with each other, so this goes back to this idea that because A and C are not communicating with each other, then it's hard to tell and synchronize, well, hey, who should talk to B first? Should I talk to B first? Should my frame go first, or should his frame go first? Okay. So here's the exposed node problem. So although B and C are exposed to each other's signals, there is no interference if B transmits to A while C transmits to D. Okay, so let's read about it. So the exposed node problem occurs under the circumstances there where each of the 4 nodes is able to send and receive signals that just reach the nodes to its immediate left and right. For example, B can do with A and C, but not with D, so on and so forth. Suppose B is sending to A. Node C is aware of this communication. It would be a mistake, however, for C to conclude that it cannot transmit to anyone just because it can hear B's transmission. So the problem is, if B is transmitting to A, in this case, C might think, oh, I can't transmit to anyone, so even though D is free over here, C would think, oh, I can't transmit to anyone just because B is currently transmitting. So it might think, oh, let me wait until B's done, when in actuality, it could just talk to D immediately. Okay. Let's get back the yellow highlighter. So distribution system. So as described in 802.11, will be suitable for a network with a mesh or ad hoc topology. And development for 802.11s standard for mesh networks is nearing completion. So this would also be interesting if 802.11s has been completed. At the current time, nearly all 802.11 use a base station oriented topology. Okay. I see a security concern with an ad hoc network because people are generally very wary of peer-to-peer communication because they think, oh, there's even a, what's it called? Oh, I just realized that the entire window thing is whiting out most of the screen. I apologize. Let's get rid of that. Huh. Interesting. Is this the window capture? Yes. That's better. Huh. Okay. Well, now you guys should be able to see more. That's good. Okay. Yeah, that would be interesting. So I think there's a Silicon Valley episode that when they're talking about their storage system and how it's some like peer-to-peer network thing. Yeah, people don't like it when you say peer-to-peer. They think leaking information if you say peer-to-peer. Okay. So let's talk about this. Which is access points. Let's talk about access points and distribution systems. So the techniques for selecting an access point, called scanning, involves 4 steps. So the node sends a probe frame. All access points within reach give a response or reply frame. The node selects one of the access points and sends that access point an association request frame, and then the access point replies with an association request or association response frame. So a node engages this protocol whenever it joins a network, as well as when it becomes unhappy with the current network or access point. So this might be because the signal from the current AP is weakened to the node moving away from it. So if you're on your phone and using Wi-Fi and you start walking away from the building, it may kick you off and go, I can barely access this anymore, so I'm quitting. Okay. So this is some distribution system, and it talks, this is access point 1, access point 2, access point 3. And so, C may belong to these 2 different spots, so it can see, say, or C may move from access point 1 to access point 2 and be able to see these things. Something like B might be able to see both 1 and 2. And then something like F would only ever be able to see access point 3. And this talks about node mobility. So you can move between these nodes. So active scanning, since the node is actively searching for an access point. So that's this idea that when you're walking around and you have your Wi-Fi antenna on, it's constantly trying to see, hey, is there somebody nearby I can connect to? And we see that 802.11, like everything we've seen, has a frame format. It's not very interesting. Bluetooth, another wireless technology. It's actually specified by an industry group called the Bluetooth Special Interest Group. A special interest group just for Bluetooth. So the basic Bluetooth network configuration, called PicoNet, consists of a master device and up to 7 slave devices. So if you have some Bluetooth receiver, you could potentially connect to 7 Bluetooth devices. And so these are typically lower range and lower power. And so a slave device can be parked, that is set to an inactive low power state, and a parked device cannot communicate on PicoNet. It is only reactivated by the master. So this is kind of like a sleep mode. And so PicoNet can have 255 parked devices, or what is that? Is that 2 to the 8, I think? Yeah, it's 2 to the 8. So one of these is a newer one called Zigbee, divided by the Zigbee Alliance, standardized at 802.15.4. It's designed for situations where bandwidth requirements are low and power consumption must be very low. So for something like IoT, this is probably more relevant. So this is this idea of Bluetooth connection. So you can have, say, some MP3 player, some tablet, some printer, another phone or tablet, and then let's say a printer. So in this case, this is 6 things. So you connect one more thing via Bluetooth. And then we'll briefly go over smartphone technologies. So like 802.11, so WiMAX cellular technology, it uses base stations just like Wi-Fi. The geographic area served by base station antenna is called a cell. So every cell tower, it's called a cell tower because it serves a cell. That's the antenna. And then we have to ensure that there's some kind of handoff. So if you're going between overlapping regions, you don't want your phone call to drop because you're getting moved to a new antenna. You want some kind of seamless transition. So they're loosely categorized by generation. I thought they were going to talk about the different things. So they have first generation or second generation or third generation. And these generally just correspond to greater bandwidth and then maybe simultaneous voice and data transmission. And then, you know, we're even at 3, 4G. Is 5G a thing? I'm not even sure if 5G is a thing. Okay. So CDMA also uses some kind of spread spectrum technology. It's typically optimized for things like bursty data, and there's no hard limit on how many users can share a piece of the spectrum. You just need to have unique chipping codes. Interesting. Okay. So let's talk about security. Everyone cares about security, right? I care about security. One of the fairly obvious problems of wireless links compared to wires or fibers is that you can't be too sure where your data has gone. So chapter 8 is going to be more for the discussion on this topic. So it seems like they're just saying that everything's in chapter 8. That isn't great, isn't it? But it looks like we've gotten to the end of the chapter. So I guess in chapter 8 we'll learn about wireless security. Yeah. I'm really disappointed. I thought they would talk about it at least. But really they just say, look at chapter 8. Okay, so what did we learn today? So in this chapter, we saw varied types of links, things like wireless links, wired links, cellular links, and we saw where those corresponded physically on a bandwidth scale, what kinds of mediums they go over. We went over the different problems, such as how do we encode bits using things like Manchester code, or NHZ, or NHZI, or 4B, 5B, or NRZ rather. We saw that we can package these things into frames, and everyone decides what their own frame format is. There's multiple standards that we can use, or that are used in practice. We saw that we can add things such as cyclic redundancy checks and other types of parity and checksums in order to get a better in order to better recover data or recognize failures to transmit data. We also saw ways to make a link appear reliable. So using things like sliding windows and concurrent channels, we saw that we can, transmit many frames at once and then only send requests back, every once in a while saying, hey, I missed a frame, or I didn't acknowledge something. And then we also saw a problem that's not relevant to point-to-point links, but for multiple access links, is how do we mediate access on a shared link? So if we run into traffic on a shared link, how do we get over that? And we saw how media access in wireless links is made more complicated by the fact that some nodes may be hidden from each other due to limited range of radio transmission. So that was a case where we may have some overlap, and everyone might be trying to send to a single node, but they can't see each other, so they don't know, hey, I shouldn't be sending now. So we learned a lot of things today. But what are we going to be learning about next time? That'll be interesting. What's next time on computer networks? With Nick from Engineering Today. A lot of questions at the end of these chapters. Wow. 57? Yikes. Okay. Internetworking. So what is this going to be on? Switching and bridging. Okay. Well, everyone, I want to thank you for stopping by today. I think we had a lovely time. I want to thank you to the 2 people that have subscribed to me so far. I think that was Beryllium subscribed to me, as well as ABD7 gave me a Twitch Prime sub. So thank you very much for that. If you guys want any kinds of special content, let me know. I'd be happy to oblige. Otherwise, hey, I'm not going to assign any homework today. In fact, I'm going to be the cool professor. I'm going to let you out early today. I may be moving the stream to the morning. I may be doing it at 4 a.m. Eastern Standard Time, just to see if I might be able to pick up a few more viewers then. Try to capture the EU markets. We'll see how that goes. But for right now, I'm going to be focusing on making some more, some more short form content for YouTube. So check it out. I'm working on logos and stuff, and I'm working on YouTube thumbnails to be more consistent so it doesn't look like such a hodgepodge of information. But I want to thank you all for joining me today. I appreciate you being here. And as always, I hope you go out there and you learn something new every day. This is Nick from Engineering Today, signing out. See you later.